This sorting algorithm is fast and efficient. It meets every mechanical target, yet systematically rejects viable objects due to an invisible flaw in its instructions. This is the paradox of machine learning. A model can achieve perfect convergence and low loss metrics during training, while remaining fundamentally broken in its logic. These automated systems increasingly govern high-stakes life events, such as the approval of financial loans or the initial screening of job applicants. Because the consequences are so significant, these models must evaluate candidates without making distinctions based on race, gender, or age. However, when unintentional bias infects the training data, the model produces outcomes that are unreliable and, in many cases, systemically unfair. Standard accuracy targets and loss measures are insufficient for detecting these failures. Building a solid model requires auditing the inputs themselves. Before any model is operationalized, engineers must rigorously examine the training data and its provenance to check for 6 specific structural biases. Optimization does not guarantee objectivity. A model is only as neutral as the human assumptions encoded into its ingestion pipeline. To understand where these flaws begin, we start with total real-world data, a dense 3D point cloud representing objective reality. Reporting bias occurs when a dataset captures only a selective, small portion of these outcomes. Huge sections of accessible realities simply vanish from the distribution. This happens when analysis disregards news articles in other languages, or when a database prioritizes studies with favorable findings over those with insignificant results. It also manifests as outcome reporting bias, like a company that only logs performance data during its most profitable quarters. Selection bias represents a failure of proper randomization during collection. Instead of a representative sample, the dataset captures only this isolated cluster of points in the corner. One common failure is convergence bias, where the method of gathering information is not representative of the broader general population. If a survey only includes the half of your customers who already purchased a product, the resulting dataset will not reflect the profile of those who chose not to buy. Participation bias further skews this collection, as gaps in who chooses to participate create additional voids in the data. These collection flaws physically warp the mathematical foundation, forcing the algorithm to learn a localized and highly distorted version of reality. Once the data is missing, the next error occurs when humans aggressively extrapolate patterns from the distorted fragments that remain. This is overgeneralisation bias, the false assumption that observations from one localized dataset will apply to every other dataset evaluating the same information. Even a massive dataset offers no protection against this if the underlying assumptions are too broad. This logic leads to group attribution bias, the propensity to generalize the truths of a few individuals to the entire group they belong to. In-group bias occurs when priority is given to those who share interests or memberships with the decision maker. For example, a manager might assume all qualified data scientists must have a master's degree because they have one, disregarding any candidates with equivalent work experience. The inverse is outgroup bias, where stereotypes are applied to those outside of one's own circle. In this case, the manager assumes that any candidate without that specific degree fundamentally lacks the necessary knowledge for the job. These extrapolation errors act as a multiplier, turning subjective human stereotypes into rigid mathematical rules. Other biases emerge from personal experiences that do not apply to more generic or global situations. This illustrates implicit bias. We frequently act in ways that are stereotyped without realizing we are applying a narrow cultural lens to the data. A North American engineer might program a computer vision system to flag the color red as a danger signal, ignoring that in Chinese culture, red represents luck and joy. This transforms an arbitrary cultural norm into an objective system parameter. After these layers of distortion are embedded, the model is finally deployed into the real world. At this stage, automation bias takes over. Humans have a dangerous propensity to favor recommendations from automated systems, even when they have evidence to the contrary. Operators often disregard accurate, non-automated data simply because the machine provides an easy, definitive answer. In this pipeline, the human in the loop becomes an amplifier for systemic bias, rather than a safeguard against it. This is the cumulative damage. We started with a pristine cloud of real-world truth, but trained our model on a tiny, distorted cluster. Because it was optimized for a corrupted subset, its logic wildly miscategorizes the actual population when exposed to reality. The model cannot detect its own bias. It can only optimize for the narrow, distorted universe it was fed. This failure pipeline is predictable: collection corrupted by selective reporting, engineering corrupted by implicit logic, and decisions corrupted by automation. Therefore, examining the training data and tracing the raw source is a mandatory step in the development cycle. You must audit the provenance of your data streams before you operationalize a single model. Success in data science is found not just in the optimization of the algorithm, but in the rigorous vetting of the data it consumes.